Welcome! In this video, we will tackle the problem smallest string with a given numeric value. We'll break it down step by step, explore approaches like brute force, and aim for an optimal solution. Let's dive in. In this problem, you are tasked with constructing a string s of length and using lowercase English letters. The string must have a numeric value equal to k, and it should be the smallest lexicographical string possible. The numeric value of a string is calculated as the sum of the numeric values of its characters, or a equals 1, b equals 2, and so on up to z, which equals 26. Additionally, a string is considered lexicographically smaller than another if at the first position where they differ, the character in the first string comes earlier in the alphabet. For example, ABC is smaller than ACD because B comes before C. If you cannot construct such a string, you should return an empty string. The input parameters include n, the required length of the string, and k, the numeric value that the string must achieve. The constraints ensure n is at least 1 and at most 100,000, and k is at least n and at most 26 times n. The output of the problem is a string s of length and that satisfies the given numeric value k and is the smallest lexicographical string possible. Let's look at some examples to better understand the requirements. In the first example, the input is n equals 3 and k equals 27. The output is AAE. This string has a length of 3 and a numeric value of 27, calculated as 1 for a, 1 for the second a, and 25 for y. Among all strings that meet these conditions, AAE is the smallest lexicographically. This means that no other valid string with the same length and numeric value would appear earlier in alphabetical order. In the second example, the input is n equals 5 and k equals 73. The output is AAs. This string has a length of 5, and its numeric value is 73. The calculation is 1 for each of the 3 a characters and 26 for each of the 2 z characters, totaling 73. This string is also the smallest lexicographical option that satisfies the conditions. In the third example, the input is n equals 2 and k equals 5. This demonstrates a smaller case where the output is AC. The string AC has a length of 2, with a numeric value of 5, calculated as 1 for and 3 for C. Again, it is the smallest lexicographically valid string for this input. The constraints for the problem ensure that a solution always exists. Specifically, n is at least 1 and at most 100,000, while k is at least n and at most 26 times n. This means that the smallest possible numeric value of the string is achieved when all characters are a, and the largest possible numeric value occurs when all characters are z. Additionally, edge cases include scenarios like the minimum input values, where n equals 1 and k equals 1. In this case, the output would simply be a. For the maximum input values, when n equals 100,000 and k equals 26*100,000, the string would consist entirely of z repeated 100,000 times. There are also specific patterns to consider. For example, if k equals n, the numeric value is achieved by having a repeated n times, since a has the smallest possible value of 1. Similarly, if k equals 26 plus n1, the string would consist of a repeated n 1 times, followed by a single z, which maximizes the value of the last character while keeping the string lexicographically small. These edge cases and patterns highlight how the constraints and numeric value requirements interact to ensure valid outputs under all conditions. To begin with, let's consider the brute force approach. The intuition here is straightforward. We generate all possible strings of length and using lowercase letters from a to z. Once we have all these combinations, we calculate the numeric value for each string. Finally, we simply return the lexicographically smallest string whose numeric value matches the given k. However, the complexity of this approach makes it highly impractical. Since there are 26 letters in the alphabet, the number of possible combinations grows exponentially as 26*n. This means that even for relatively small values of n, such as 10, the number of strings to process becomes astronomically large. Additionally, the space required to generate and store all these strings is also exponential, making this approach infeasible for larger inputs. This trade-off highlights how brute force is an inefficient choice for this problem, especially given the constraints. Now, let's explore the greedy approach, which is significantly more efficient. The key idea is to start with the smallest possible string, consisting of n a's, since the numeric value of a is 1. This gives us an initial numeric value of n. From there, we increment the characters, beginning from the rightmost position, to increase the numeric value while ensuring the string remains lexicographically smallest. Each character can be incremented up to z, which has a numeric value of 26. We stop as soon as the numeric value of the string equals k. This approach is much better in terms of complexity, requiring only a single pass through the string. The time complexity is O, n, and the space complexity is also O, n, as we only store the output string. However, while this method is efficient and adheres to the problem constraints, it involves iterative adjustments to the string, which can still be optimized further. Next, we have the direct computation approach, which builds on the greedy logic but eliminates unnecessary iterations. The intuition here is to directly compute how much each character in the string should contribute to the numeric value. First, we initialize the string with n a's, giving a minimal numeric value of n. Then, we calculate the remaining value, referred to as extra, which is simply kn. Starting from the rightmost character, we distribute this extra value by incrementing each character as much as possible, up to a maximum increment of 25, since z equals 26. Once the extra value is fully distributed, we convert the numeric values of the characters back into their corresponding letters, giving us the final string. This approach is both time and space efficient, with a complexity of O, n. It avoids iterative adjustments and guarantees correctness, making it the most efficient strategy for this problem. Finally, the chosen strategy is the direct computation approach, due to its efficiency and clarity. The key insight here is that we can pre-compute how to distribute the required numeric value across the string without resorting to iterative adjustments. By starting with the smallest lexicographical string, which is NAs, and working backward, we ensure both the smallest lexicographical order and the correct numeric value in linear time. This approach stands out compared to the alternatives. While the greedy method is intuitive, it involves more steps than necessary, and the brute force approach is entirely impractical due to its exponential complexity. The direct computation method, on the other hand, minimizes operations and ensures correctness, making it the optimal solution for this problem. It is particularly well suited to handle the problem constraints, such as 1 equals n equals 10⁻⁵, which demand an O(n) solution. By balancing efficiency with correctness, this approach effectively addresses all aspects of the problem. To solve this problem, our task is to construct the lexicographically smallest string of length n such that its numeric value equals k. The numeric value of a string is the sum of the positions of its characters in the alphabet, or it equals 1, b equals 2, and so on up to z, which equals 26. Understanding the constraints is crucial here. The smallest string of length n is made entirely of a, which has a numeric value of n. On the other hand, the largest possible string is made of z, giving a numeric value of 26*n. If k is less than n or greater than 26*n, it's impossible to construct such a string. The key insight for designing the solution is to use smaller letters like a as much as possible to minimize the lexicographical order, while only adding larger letters like z when necessary to reach the required numeric value. To begin, we initialize the result as a list of characters, corresponding to the smallest numeric value of n. We then subtract this value from k to determine the remaining value that needs to be distributed across the string. This forms the basis of our solution strategy. Once we have the remaining value, the next step is to distribute it across the string to meet the numeric target while keeping the string lexicographically smallest. To do this, we start from the end of the string and move backward. By prioritizing the rightmost positions for higher values, we ensure that the overall order remains minimal. For each position, we calculate the maximum additional value it can contribute, which is 25, corresponding to the difference between z and a. We then take the smaller of the remaining value and this maximum possible addition and update the character at the current position accordingly. The remaining value is reduced by the amount added, and we continue this process for earlier positions. If at any point remaining becomes 0, we can stop since no further adjustments are needed. Finally, after distributing the value, we convert the list back into a string and return it as the result. This method ensures that the string is constructed optimally to satisfy both the numeric and lexicographical constraints. The design of this solution is driven by a greedy approach, where we systematically distribute the remaining value across the string from the rightmost position to minimize the lexicographical order. By always prioritizing smaller letters at the lower indices, we ensure the string remains as minimal as possible. This approach is highly efficient because we stop distributing values as soon as the remaining value reaches 0, avoiding unnecessary operations. The key data structures involved include the result list, which allows in-place updates for constructing the string, and the remaining variable, which tracks the value still required to meet the target k. When analyzing complexity, the algorithm runs in O(n) time since it iterates through the string once, and it uses O(n) space for the result list. This makes the solution both time and space efficient for the problem constraints. Let's walk through an example to see the algorithm in action. Suppose the input is n equals 5 and k equals 73. First, we initialize the result as and calculate the remaining value as 73, 5 equals 68. Starting from the last position, I equals 4, we add the minimum of remaining in 25, which is 25. We update result, 4, to z and reduce remaining to 43. Moving to I equals 3, we again add 25, update result, 3, to z, and reduce remaining to 18. At I equals 2, we add the remaining value of 18, update result, 2, to s, and set remaining to 0. At this point, no further adjustments are needed, and the final string is os. This example demonstrates the efficient distribution of values while maintaining lexicographical order. Edge cases to consider include when k is less than n, which makes it impossible to construct a string, or when k equals n, where the result is simply a repeated n times. For k equal to 26 n, the result would be all z. By handling these scenarios, the algorithm remains robust and reliable. The problem requires us to construct the lexicographically smallest string of length n with a numeric value of k. Here's how the solution works. 1. Initialization. We start by creating a list result of size n filled with the character a. This is because the smallest lexicographical string consists of all a characters, and each a contributes 1 to the numeric value. We then decrease k by n to adjust for the initial numeric value contributed by these a characters. 2. Filling the string. To achieve the desired numeric value while maintaining lexicographical order, we iterate from the last position to the first in the result array. This ensures that we prioritize the largest contributions to the numeric value at later positions. 3. Updating characters. For each position, we calculate the maximum value we can add to the current character without exceeding the remaining k. The maximum value for any character is 25, corresponding to z(a). Using chr and ord, we update the character at the current position to reflect this value. For adjusting k, after updating the character, we reduce k by the value we added. If k becomes 0, we can terminate early since the required numeric value is achieved. 5. Returning the result. Finally, the result list is joined into a string and returned. This approach ensures that the string is constructed efficiently in O(n) time, as we iterate through the positions once and make constant time updates for each. The use of the greedy strategy ensures that the string is lexicographically smallest while meeting the numeric value requirement. Here, we begin with the Java implementation of the solution. The method getSmallestString takes two parameters, n, which represents the length of the string, and k, the numeric value we need to achieve. First, we initialize a character array result of size n with all elements set to a. This is because each a contributes a numeric value of 1. Then, we reduce k by n to account for this initial numeric value provided by the array of a. Next, we use a loop that starts from the end of the array and moves toward the beginning. For each position, we calculate the maximum value we can add to the current character without exceeding k. This is done using math.min, k at 25, since the difference between z and a is 25. We then update the character at the current position using this value and reduce k by the same amount. If k becomes 0, we know the string is complete, and we can exit the loop early. Finally, once the loop is done, we convert the result character array into a string and return it. This ensures that we produce the lexicographically smallest string that satisfies the given constraints. By starting with all characters as it and only increasing their values from the back, we ensure that the smallest possible string is generated. This approach is both efficient and intuitive, as the loop iterates at most n times, and each operation is straightforward. The result is a solution that constructs the desired string while adhering to the constraints given in the problem. To solve the problem for example 1 where n equals 3 and k equals 27, we start by initializing the result string with 3 a's. This setup gives the string an initial numeric value of 3, since each a contributes 1 to the total. To account for this initial value, we subtract n from k, resulting in a new value of k equal to 24. Now, we begin updating the string from the last position, which is index 2. At this position, we calculate the additional value that can be added without exceeding the constraints. This value is the minimum of k and 25, which in this case is 24. We then update the character at this position to y, as y corresponds to an additional value of 24. After updating the string, we subtract this value from k, leaving k equal to 0. At this point, the loop terminates since there's no remaining value to distribute. The final string is AAE, and that becomes our output for this example. In example 2, where n equals 5 and k equals 73, we start similarly by initializing the result as a string of 5 a's. This gives an initial value of 5, so we subtract n from k, leaving us with k equal to 68. Starting from the last position, index 4, we calculate the additional value for this position, which is the minimum of k and 25. Here, it's 25. We update the character at index 4 to z, which adds 25 to the string's total value. Subtracting this from k leaves us with k equal to 43. Next, we move to position 3 and repeat the process. Again, the additional value is 25, so we update the character at index 3 to z. After this step, k is reduced to 18, and the intermediate string is now AAs. Continuing with the same approach, we now update position 2. Here, the additional value is calculated as the minimum of k and 25, which in this case is 18. We update the character at index 2 to s, since s corresponds to an additional value of 18. With this update, k becomes 0, and the loop ends because no further value needs to be distributed. The result string at this stage is os. Finally, we join the characters to form the output string, which is os. This is the smallest string that meets the given numeric value of 73 while using 5 characters. Now, let's examine example 3, where n equals 4 and k equals 30. Again, we initialize the result as a string of 4 a's, which gives an initial numeric value of 4. Subtracting n from k leaves us with k equal to 26. Starting from the last position, index 3, we calculate the additional value as the minimum of k and 25, which is 25. We then update the character at this position to z, adding 25 to the string's total value. After this update, k is reduced to 1. Next, we move to position 2. Here, the additional value is 1, so we update the character at index 2 to b, which corresponds to adding 1 to the total value. At this point, k becomes 0, and we terminate the loop since no further adjustments are needed. In the final step, we join the characters of the result string to form abs. This is the smallest string that satisfies the constraints of having 4 characters and a total numeric value of 30. Therefore, the output for this example is abs. The time complexity of this algorithm can be broken down into several steps. First, we initialize the result array with n elements, each set to O. This operation is straightforward and takes n time since the array has a fixed size of n. Next, the main part of the algorithm involves iterating over the array in reverse, starting from index n1 and ending at index 0. This loop executes at most n iterations, and within each iteration, we perform 3 constant time operations, calculating the add_value using the minimum of k and 25, updating the corresponding character in the result array, and decrementing k by the add_value. Since these operations are all O(1), the total cost of the loop is proportional to the number of iterations, which is O(n). Together, these steps determine the overall time complexity of the algorithm. After constructing the result array, the algorithm converts it into a string using the join method. This step processes all n elements in the array, resulting in an O(n) operation. Combining this with the previous steps, the dominant contributors to the time complexity are the loop and the string join, both of which scale linearly with n. Therefore, the overall time complexity of the algorithm is O(n). Now, moving to space complexity, the primary factor is the result array, which requires O(n) space as it stores n characters. The algorithm also uses a few auxiliary variables like k, @_value, and I, but these consume constant space, or O(1). Consequently, the total space complexity is dominated by the result array, making it O(n). To better understand the efficiency of this approach, let's compare it to a naive or brute force method. A naive solution would involve generating all possible strings of length n and numeric value k, then selecting the smallest string lexicographically. However, this would require exploring an exponential number of possibilities, with a time complexity of O(26 to the power of n, which is computationally infeasible for large values of n. In contrast, the optimized approach leverages a greedy strategy to directly construct the desired string in O(n) time and space. By updating the string from the end, we ensure that the result is both lexicographically minimal and satisfies the numeric value constraint. Additionally, it's important to note that the time complexity remains O(n) in the best, average, and worst cases, as the loop always performs the same number of iterations regardless of the input conditions. The mathematical justification for the O(n) time complexity is rooted in the fact that the loop iterates exactly n times, with each iteration involving only constant time operations such as arithmetic calculations and array updates. This means the total work done is directly proportional to n. Similarly, the space complexity is determined by the result array, which stores n characters and requires O(n) space. Since no other part of the algorithm uses significant additional memory, the space complexity is also O(n). This consistent scaling in both time and space ensures the algorithm is highly efficient, even for large inputs. When tackling this problem, there are a few common mistakes to watch out for. First, misunderstanding the problem constraints can lead to issues. For example, if you overlook the maximum values for n or k, or fail to consider whether duplicates are allowed, your solution might perform well for some test cases but fail for edge cases. This often results in exceeding time complexity limits or producing incomplete outputs. Another frequent mistake is relying on inefficient brute force approaches. While these might work for smaller inputs, they are not scalable and will likely time out for larger datasets. Instead, you should aim to optimize by pruning unnecessary paths or leveraging sorting to reduce computational overhead. Finally, a critical error is ignoring lexicographical order when required. If the goal is to create the smallest or largest string, your solution must prioritize characters appropriately. Overlooking this detail could mean your solution appears correct functionally but fails when correctness is tied to the order of characters in the result. Another common pitfall is off-by-one errors, which can occur when handling loops or indices. This often happens when transitioning between 0-based and 1-based indices or when iterating through character ranges. Such errors can lead to incorrect results or even runtime crashes, so always double-check your bounds. Additionally, failing to test edge cases is a significant oversight. For instance, scenarios like n equals 1 or n equals 10⁻5 can reveal flaws in your implementation that typical inputs might not expose. To avoid these issues, thorough testing with both minimum and extreme values is crucial. From an interview perspective, it's important to focus on clarifying constraints early. For example, confirm the maximum values for n and k with your interviewer to ensure your approach is feasible. Starting with a brute force solution can also help you understand the problem better and pave the way for optimization. If lexicographical order is a requirement, consider using a greedy algorithm or a priority queue for efficiency. And don't forget to clearly explain trade-offs between approaches, such as time complexity versus space complexity, as this demonstrates your analytical skills. To deepen your understanding, it can be helpful to explore related problems. For instance, LeetCode 31, next permutation, focuses on generating the lexicographically next permutation of a sequence, which is closely tied to ordering logic. Similarly, LeetCode 402, remove k digits, involves forming the smallest number by strategically removing digits, a task that also prioritizes optimization for minimal values. LeetCode 60, permutation sequence, challenges you to find a specific permutation in lexicographical order, while LeetCode 1081, smallest subsequence of distinct characters, shares the goal of forming the smallest lexicographical subsequence. Considering alternative approaches can also be useful. Recursive backtracking is a straightforward method that's easy to implement and understand, but its exponential time complexity makes it impractical for larger inputs. On the other hand, a greedy approach is highly efficient for problems emphasizing lexicographical order, though it may require pre-processing like sorting to work effectively. Dynamic programming is another alternative, particularly well suited for problems with overlapping subproblems. It allows for efficient solutions but can be more challenging to implement and debug during time-constrained interviews. This makes it a less popular choice unless the problem explicitly benefits from this approach. Finally, the priority queue method is an excellent option for maintaining order efficiently. It's especially useful when you need to repeatedly extract or modify the smallest or largest elements. However, its higher space complexity, due to the use of a heap, might be a drawback in memory-constrained environments. Each of these methods has its strengths and weaknesses, so understanding the trade-offs will help you determine the best approach for the specific problem at hand. Great job! We reviewed the problem, discussed multiple approaches, and learned some valuable strategies. Keep practicing, and don't forget to subscribe for more problem-solving tips. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!